Good morning, everyone. We will be starting the session in another 2 minutes. Kindly be seated. Good morning, everyone. Please be seated. We are about to start the session. So, I'll call you soon. Good morning and a heartfelt welcome to day 2 of ICCMS 2025 at the prestigious IIT Tirupati. Set in a city known for its cultural richness and academic spirit, IIT Tirupati continues to provide an inspiring backdrop for our ongoing exchange of ideas. Yesterday, we had an enriching start with insightful keynote addresses, engaging plenary talks, and valuable interactions among researchers and professionals. We thank you all for your active participation. Today, we look forward to an insightful lineup of sessions and discussions. Each presentation will be allotted 35 minutes, followed by a 5-minute question and answer session to ensure meaningful dialogue and reflection. For today's plenary session, we are honored to have Professor Baltazar Novak as the session chair. Professor Novak is an eminent figure in structural and civil engineering, currently serving as the Deputy Director of the Institute for Lightweight Structures and Conceptual Design at the University of Stuttgart. With a career spanning over 2 decades, Professor Novak has made foundational contributions to the understanding and design of pre-stressed concrete systems, seismic resilience in structures, and advanced bridge engineering, including corrugated steel web composites. A graduate of the Technical University of Darmstadt, where he also earned his doctorate in 1995, his research has influenced European bridge design codes and life cycle based infrastructure planning. Internationally engaged, Professor Nowak has led collaborative initiatives across continents and is widely recognized for his academic leadership and impactful publications. We now invite him to take the stage and guide us through the upcoming talks.
Thank you very much for the introduction. Good morning, everyone. I hope you had a good evening yesterday and a good night, and you could recover somehow to have enough strength for today. Today is the second day of our conference on construction materials and structures, and we just talked a little bit. Gianluca Ranzi and myself, we talked a little bit about before, and we have seen that there's a big overlap of interests and of research areas. So I'm very proud that I'm able to announce you as the first plenary speaker this morning. He is chair of the Center of Advanced Structural Engineering at the University of Sydney, but originally he's from Italy. So his heart is beating in two different countries. But maybe India will also come now into the picture. He's a really expert in structural engineering, and he's working in concrete and composite structures. He's focusing on sustainability and the assessment of existing structures, which comes more and more into the focus in these days. He's also active in the development of international design standards, and he has made significant impact through research and professional service. So I'm very happy that I'm able to announce you, and please come on stage.
Good morning, everyone. Thank you very much for the kind introduction. I would like to first of all thank the organizer, because we are coming here, we're just stepping in and join the conference, but we don't see all the activity going behind, and it's been also been happening in all previous weeks. So it's a real pleasure to be here, and thank you very much for the wonderful organization. Today's presentation will come up soon, and it's about, I would say, trying to give a justification on why we should be trying to use advanced modeling. And I will try to do it from a very practical point of view. Yes. Thank you. Wonderful. Thank you very much. And maybe just linking back to what the chairman, Professor Novak, previously said, is there is a lot of things we were considering before. There is a lot of, I think, happening in the space of civil engineering. And sometimes I think we are not, I would say, sufficiently, let me call it arrogant in a good way, about ourselves. For example, if you are going to a different country and you want to enjoy beautiful food, you're happy to pay for it. But when it comes down to structural engineering, for example, if you think about projects, they're really given at cost. So I think there is a process there, which is education, not just of us as a discipline, but also of the market. Because sometimes if you think of building, is this building valuable for the value that you're paying for? At the moment, the market is driven with a certain number of things. I'm going to flag just a couple of ones during the presentation. And I think that's really the key, the heart of the issue, is who is the client eventually. So going back to the technical part, and so I would just like to introduce a few concepts related to concrete. It's going to be basic knowledge, but I will say, just to ask a few key questions to say, should we do more? And if we do more, is that going to be advantageous to us? And I'm just going to bring up a few items, a few specific scenarios where through experimental work, we can demonstrate, and in some scenarios, advanced modeling actually is the way to go. And then if you step back from those results, you can start to think, well, is it worth it to take this also in a design space? Is there really an opportunity there to improve our design guidelines, the process? And just some final concluding remarks. So first of all, just some brief introduction on concrete materials. I think creep and shrinkage, many of you already are fully familiar with that. And just touch base just on a couple of things, is that really creep is taking place when you've got a sustained load applied to a concrete element that stays there over time. And it's really, usually we have two features. One is called the basic and one drying. Yeah, one basic, one drying. And basically, it's got to do with the fact that one is happening without exchange of moisture with the soil environment. The one is taking place with exchange. And similar things with shrinkage. So shrinkage is really time-dependent change in volume for the concrete. If you think about, what are the key factors affecting time-dependent behavior, you can really usually, they're well understood, they're already codified. They have environmental effects, vectors, material properties, geometries of the cross-section, it affects how it dries, and also boundary conditions, which actually, the kind of interaction of the element with the surrounding space. So, for example, usually, if you look at time-dependent sort of behavior, usually have if you sort of imagine, just simplified, I'm just showing this because I want to demonstrate something in the coming slides, is usually if you actually assume a sustained stress applied to the concrete constant over time, it's very unlikely. In reality, in concrete, nothing stays constant unless it's unreinforced. But I would say stays constant, then usually you can draw the change in deformation, which is on the vertical axis, over time, which has got the initial part due to shrinkage, and then creep kicking in, and so you've got these time-dependent deformations taking place. If you want to model this, usually the simple way, in the way codes are usually handling this, they sort of give you guidance on what's called the creep coefficient, which is this phi term. And usually they allow you to, from this phi term, you can calculate what's called the creep function, so this J function here. And I'm just touching base on this because I want to demonstrate something from standards. But I will say it's a very powerful function, because this creep function here basically allows you to calculate the strain at any point in time due to a sustained stress applied at a particular time. And usually when you're doing time analysis, time naught or time zero is really the time of first application of the load. If you then model this and you want to sort of account for variation in changes, usually you rely on the principle of superposition. You can start to sort of add the contribution of different changes in stress, and you can actually push this to what it is, the integral type creep law, which is basically a continuous variation. That's what's really happening in real structures. So if you sort of now want to sort of solve this, I mean, usually there are two major approaches used. One's called the integral type and the rate type creep laws. They're basically coming from the same thing. They're very similar. I would say they're equivalent. It just is how you implement them, it changes. And I'm just going to talk through just a second for this representation here. So this actually is the typical equation for integral type creep law, which means this term here just represents the deformation. Graphically, and I think that's what's useful here, is that it will be the deformation is the area under this curve here. Why? Because if you sort of rotate your head and you look at sort of the bottom quadrangle here, you've got the variation of stress over time. Time is here. So this will be a typical variation of stress. And here you've got all the creep functions that first load application. And if you bring them together, you actually can this nice graphical interpretation of what is the deformation over time, which I think it's very useful when you want to start to understand things or see things. I think it's good to always visualize things when you're trying to address problems of this kind. So what I would like to highlight is that usually in codes, whether it's spelled out or not, it's implicit that we're using the effective modulus method, which is a simplified approach, which is fine. I'm nothing against it, but actually it's a question of how useful it is. So if I now go back to our previous definition, so in the integral we were looking before, that actually allows you to calculate the deformation, is basically when you implement it through the effective modulus method, you're simply approximating this integral here. And it's integrated by sort of a term multiplying the stress at time t. So as you can see, if you got an increase in stress history, you will be overestimating the area. So this actually is the area. So it's bigger than the area you had before. And in a decreasing stress history, you will be actually underestimating, the deformation. So then the question that we will ask ourselves is actually the right way to do it? Is this actually the right approach we should use all the time? And I'm not here to say it's not because it's simplified, because a simplified good model is always wonderful. But it's a question, there are some scenarios I'm going to talk them through in a second. Also, just wanted to highlight is that, so I would say it becomes important to try to push further serviceability in those scenarios where serviceability criteria are actually those governing the geometry of the members. And there is a lot happening at the moment in the space, especially with new concretes. And also when there is environmental conditions actually play a role there. And I just thought to highlight this IAPS SED publication. We're actually just focusing on time-dependent behavior of composite structures. And the idea here was really to bring it from materials to applications. We got some case studies on real bridges and real building applications. And one issue which I would like to flag, going back to what we were saying earlier, was that we had a lot of problems in, for example, in getting the calculations for the building, calculation on the serviceability mistake, not because the companies were concerned about sharing technical information, but because the developers, so we're talking about who was driving the investment, didn't want to have any numbers on the market, so in the public domain, because they were scared they will affect the real estate value. So there is actually a chain which goes beyond the technical, I think, just justifications. And of course, there are legal implications if you start to write out also results and measurements. So now going back, I'm going to try to skim through a few scenarios. I'm going to try to be sort of as fluent as possible. I hope you will enjoy. Personally, I love this test. So for me, it's a pleasure, but not everybody, I would say, shares the same fun for some tests. So the first scenario I'm going to talk about is basically separating creep and shrinkage effects in composite beams. So these are basically a series of tests that we have done on composite beams, so steel concrete beams, and these are sustained loads. We did various tests, and what I would like the purpose of the work here was really to understand what's really happening at the shear connection. So basically, the interface between the concrete and the steel. And I'm just going to present some selected scenarios to show why advanced modeling then becomes useful. So in this case, for example, you got 3 beams. I'm just selecting the 3 main scenarios. So just typical simple super beams, very simple. And this is the typical cross section. This, I will say, is a typical beam you have in a flow system in Australia. Usually we try to do full scale when we can, because the composite action, because the shear starts, if you start to play with dimensions, you have to be very careful, I would say. So, so basically what we are having is got 3 samples, and I'm just flagging this because of the results I'm going to show in a second, is we got cast and unpropped. And so basically meaning that if it's unpropped, the sustained weight is not carried by the concrete. And then in one case, we leave it completely unloaded, so just do the shrinkage. One actually put some sustained load. In another case, we cast it prop. So how do we do this? So this is the typical loading scenarios we apply. So it's actually, we're trying to resemble a continuous load. We don't put the load on top, so the shear connection on purpose, so that we still want to reproduce as much as possible a typical scenario of a flow system. There was some issues on putting loads on top, but I won't enter in that. And this is basically, and what I want to highlight here is that when you do advanced modeling, maybe you have to start to come up with test setups to allow you to see through your advanced models. Otherwise, you start to have a lot of results, and it's very hard to really pitch whether or not the advanced model is capturing the results. So in this case, for example, we set up this simple frame system to create a scenario where we cast and prop. So actually, we got this frame is attached to the web. We put the formwork on top of it. We cast it, and then we remove the sort of elements. And we did simple things. I would say it's common sense. Sometimes good structural engineering is about common sense. We sort of as you load them, to unload them, we just release some shims, and it's worked perfectly well. And another thing actually that we did because I think is needed, when you start to do setups, you need a constant load when you want to look at creep, for example. And usually, who's done tests on creep rigs, you know that the typical creep rig is it's got a pump. You have to go there every often, especially when you start every 6 hours, 12 hours even. And the idea was, do we need to do that? I mean, can we just switch it to something that actually is person-free? I mean, why do you have to have someone always slave of the test? And so basically, we spent some time. This, I think, I would say for me, was one of the hardest test rigs I've done, because we spent a lot of time in changing the jacks. So basically, there was actually put a sustained load, like a self-weight, piece of steel, piece of concrete, against a smaller jack, small ram, builds up a pressure, and then apply the pressure through a larger jack, and they can keep it loaded. So we tried different sleeves, and then we actually got in our system where actually once you push up the weight, it stays on for 3-4 months. So it's brilliant, it's very comfortable. And we applied that to different scenarios. So in this case, for example, the test rig that we did for pusher test in a long term. And I just want to show you that when you do advanced modeling, you have to push the experimental part as well, because otherwise it becomes a numerical exercise. And this is the interesting point, in the sense that these results are just sort of now already post-processed. So in this case, you've got the 3 beams we saw before. In this beam, we got only the shrinkage effect. In these 2 cases, we got only the creep effect. So it's been already manipulated. And what I want to highlight here is that the continuous line is basically assuming a linear elastic shear connection. So it's just a spring, the interface between concrete and steel. And the dashed line is a time dependent. So we got sort of a creeping of the shear connection, which actually has got to do with the 3-dimensional behavior of the concrete near the shear connector. And as you can see, shrinkage and creep actually got opposite effects. So in a way, without actually trying to visualize more with a model, more refined model, you will never be able to distinguish that creep is sort of overestimating or sort of going above, I would say, the inelastic response. And when you look at shrinkage, actually it's going below. Because usually you look at the results always together. And in this sense, we're able to develop the equation. And I will say you will not be able to get this kind of insight without actually doing the suitable test and having the models, suitable for that. And this actually will apply to any connection that, nowadays, you see a lot of buildings having very fancy connections where the shear connection is really working there. And we apply this, then you can start to really play around. Once you got the loading system set up, you can really do many, many things. Then I would just like to move on, is just to some models. so we actually pushed, line elements mostly. And the reason is that sometimes to set up these three-dimensional, shell solid elements, it's quite complicated. It's very hard to check and it's very hard to post-process them. So we actually spend a lot of time and fun, I would say, in developing line elements. And we really had plenty, we really played a lot. And we look at, for example, cases where you got composite beams with shear connection, or for example, even allow, deformability like you will have in thermal structures. And this is, for example, some work that we did from generalized beam theory. So it actually is originally from Germany in terms of origin of this theory. And but actually became very powerful. Just to show you the effect of it is that if you got sort of a box girdle like this, if you just model it, just to give an idea, just linear elastically, you can see you can capture. So these are comparison displacements between the line element that we produce and sort of a very refined Abacus shell element model. You see, actually, they perfectly match. Of course, the deformations are exaggerated here just to show them, and same thing is applied to stresses. So actually, there is a lot of power that we can push in that we have available, and we really need to use it in the right context, I will say. So this is, for example, to look at shear lag effects. Shear lag is basically the behavior. You have a typical flow beam, but can be a wall or other systems where basically you have higher stress concentrations near the shear connections, or where you actually have loading coming through thin elements. And usually in design, we just use effective width. And if you want to, create elements that you can do, for example, very good, very quick design checks calculations, you can sort of start to refine your models to account for the shear deformability of the slabs or combine them with, whatever deformability you want to pick up also in the steel elements. And you can then, for example, you have bridges like these, you can really run very simple checks by just using, as a user, line elements. Now, these line elements, of course, are not just the typical line elements, they're enriched. But from a user's point of view, it's very easy to implement. And in this case, we'll be sort of matching, comparison, between shell element model and sort of the line elements. And you see the results very well match. I don't want to sort of spend time in showing you every single graph, but it's just really the concept here that I'm trying to get across. So in this case, will be, so before was displacement, these are stresses. Sometimes, both, they're quite, stresses especially are quite hard to get. And again, you got a variation here of stresses in different locations. So in different stages of the deck. Again, when you got complex geometry, we can also set up models to actually manage that. And again, following the same process, you can really capture those behaviors. Now, this becomes important because, for example, I had a conversation with design engineers that they do design checks of bridges. And not always is very clear that the implication of deformations on the bridge, for example, when they're doing sort of the final checks, they put, say, some tracks or heavy loads on the bridge. Sometimes they sort of misinterpret the deformation because, for example, they ignore shear deformation. It's actually quite important in these bridges. And these models, they capture it very well. So they're just, to demonstrate these are sort of very useful model. This now is a bridge in a beautiful part in Italy. So it's a composite bridge. And the span, the longest span is around 90 meters. And it's basically just a model. And I would say it's a very practical approach here, for example, to decide what is your casting sequence that you should use. So in this case here, for example, you can run, the constructor, for example, could say, I just want to cast from one side to the other one. While, for example, if you go in a differential sort of casting sequence, you actually can have better effect for the concrete. So usually the idea will be cast usually on the sagging moment region first, and then go back and do the hogging moment region. That will really help you a lot. It just is a principle. But if you look in terms of results, you will see, okay, so these are the typical sort of platforms moving across the bridge actually for the casting sequences. And if you sort of look at now some small scenarios in a parametric style scenario, you see that if you just take some dimension and just picking up some dimension just to play around these spans. So if you actually have, always 4 spans, but they varying spans, these are the typical results you will get. So if you have optimized casting, your stress distribution along the bridge, the average is always well below the one you are in continuous casting. In continuous casting, you always have the highest sort of stress at the supports. And if you actually, this sort of behavior doesn't change, for all the spans will still be there. And if you now look at, for example, the first week, after casting or after 5 years, in this case, for example, we didn't include cracking in the sense that what we are comparing, at least for this particular study here, is really have a sense for which one, what is the implication one from a really design point of view. Once you start to introduce cracking, you have to be very careful how you manage, I would say, the hypothesis. It can be done. It's not an issue. And this is, for example, the other issues in relation to what is the tensile creep behavior. And if you increase the value for fine tension, for example, you would just have, of course, the stress in the steel, in the concrete in tension will release quicker, and therefore actually will have even less stresses. And so this is just to say it's worth using this, because what are the main advantages here? The main advantages, and this is now for the bridge you saw before, is that you're pushing the peak stresses on the concrete near the second moment regions, actually, which is fine, from a sort of modeling point of view. And what you're sort of getting away, you're getting away from the stresses you will have in the bridge. So these are plots of without traffic loads. These are just really looking at the shrinkage effects. And again, you can see at the supports, and you have a big difference. If you look at here, the support, so the red will be the continuous cast, and the support is really, that's really where the issue is. At the midspan, I would say there is not, it's a small difference, but keep in mind, there is a lot of variability also in the concrete properties. So the idea is actually, if you want to push down this path, I will say there is a lack, I will say, space in the software, domain, in the sense that there is software houses, they're not always very keen to push these kind of models, also because they're very hard for them to post-process, to really manage, to maintain. Now, I would like to move to another scenario, and this is now a very common floor system in Australia. So if you've been to Australia, if you're into any car park, it's always a post-tension floor. In most of the buildings, tall buildings in the city, say Sydney, for example, will be, post-tension floor, composite floors. And what actually has been happening is that in this kind of post-tension concrete floor, usually there's been a trend in the last, I would say, 10, 15 years to actually replace timber formwork with the steel sheeting and just leave it there, just to speed up construction. And we've been involved in a project where basically we've been asked by a number of companies, Art was involved in that, is basically to look at this and to say, can we take advantage of the composite sheeting, of the steel sheeting? So actually, when we start a project like this, we usually start with some tests that just demonstrate to us what is happening. So we had a lot of samples of this type where we actually tested simply supported post-tension slabs, and we did some unreinforced concrete measurements on just to measure the shrinkage behavior. So let's say, I'm just going to show you now some selected test results just to make you see through the issue. So for example, let's say you've got a simply supported slab. Again, simply supported is a gift of a test to actually see through, because it doesn't have the complexity of the continuity that, of course, you have in reality, but at least you can isolate things. And we had 3 identical samples. The only difference was we put the sheeting on 2 samples. So if you look at, one thing as always, I like to show samples before casting, because there is a lot of work in the preparation of the samples, and we never actually shared it. And usually, once you cast it, it's gone, it disappears. And in terms of details, what actually we did is to resemble the true detail of the steel deck on site. We actually stopped the sheeting before the support so that there was no friction between the sheeting and the concrete. And these are just the information basically for the setup. So these are usually the aspect which is interesting is that at least the trend is that to really apply the pre-stressing 25% in the first day or first couple of days, and then the remaining after a few days, 75%. Now, if I can mind to look at these results here. So here you got the 3 samples, the 3 sections before. So you got 3 samples, simple supported. So these are the results for the concrete one. So the first one, which is exposed top and bottom. Now, can I just ask you, if you sort of imagine now, you've got these other 2 samples here. If I have to plot them on top of this curve, how far would you see them? How far would you measure them, from here? And these are the results. So you see, here is the sort of solid slab at the bottom here. That's a solid slab. And here are the composite, slab. Keep in mind, the only difference is the sheeting. And here we are talking about 20 millimeter deflection already after, a few months, 7 months. So this actually has got to do, and what we did here, we also then isolated and trying to predict these behaviors by putting different surface conditions on the unreinforced concrete samples. We're just keeping there over time. And it's got to do with actual drying conditions. So when you actually dry from the top and bottom, or if you just dry from one side. So in the case you dry from top and bottom, you can have a shrinkage profile of this kind. In reality, you can approximate it as a total information, for design purposes, just to be a linear, constant deformation, which actually reflects the total deformations that you will have in a sample if you look at the monitoring. And when you got the sheeting at the bottom, so it's sealed, and when you do this test, you just put some plastic to seal it. You create this kind of different gradient, which actually is cause of that additional deflection that you saw before. So in reality, we confirm that what you do in the reinforced concrete design is fine, but when you go into composite slabs, you need to move really to a shrinkage gradient. We also applied some other samples where we put in one particular one, we put curing compound, which actually it's a sort of a liquid that you put on top of the slab to actually stop it evaporating. And what you can see here, these are just some plots of some of the test setups, some of during preparation. But you can see here, the actual curing compound on the top will actually reduce the reflection. So it's sort of helping. But again, curing compounds, if you look at the data sheets, are really only viable for maximum a year or a couple of years. So you wouldn't want to specify this in design. And also how you apply them is very variable. So it's not something that you can really specify from a structural viewpoint. But it's got an effect. Again, also in this case here, if you apply the uniform shrinkage that you would usually will do if you actually were not thinking of the shrinkage gradient, you will be completely underestimating the reflection. You will be quite a lot way out. And you saw in the test before we are just having the solid slab. And additional slabs, just to show you a final remark on this domain, this space here, is that if you sort of look at now composite slabs, you go simply supporting and continuous, and we just have now the same profile. All what we change now is basically the drying condition, the surface condition that we have on the top. And so basically, I'm going to show you the results now for one sample, which is basically composite slab with the chicken at the bottom, sealed on the sides, and another sample actually sealed everywhere on the top. So if you look at these results here, so we're looking at this simply supported beam, 3-meter span is typical for this kind of dimensions. So if you actually sealed it at the end of the day of casting, this is actually where you go. Why do we do that? Because we want to eliminate all the drying effect. The idea is really, you can really kill time effects a lot if you actually work and sort of limit your drying effects. If you actually keep it sort of exposed on the top, you actually build up all these deflection here, and again, it's due to the gradient you saw before. This sample here that stopped here, we actually kept it exposed up to 37 days, and then we seal it, representing what you will have really in a construction site where actually you have your casting, and then eventually you go do sort of your furbishing of the building. So can I ask you again to imagine, what would you expect? You got it exposed up to here, and after this point here, you seal it. So after this point on, it's sealed. So where do you go? Will you go higher here? Where would you expect it to go? It actually reduced the reflection. So it's something which was actually quite interesting. And we had, I'm not going to go through the details here, but actually this is related to the humidity profile through the concrete thickness, because we're having some sense. It's a very difficult measurement to do, I would say, humidity measurement. So it's an approximated one. But what we could see here is that once you seal it, it will change the humidity profile, which actually what drives time effects. And that was the reason why actually it was coming down. We had the same similar thing with the continuous samples. And again, these are sealed, the red ones. You got two lines because we got two spans now, it's continuous. And so in this case, you got the two spans, red sealed, green exposed on the top for the entire period. And the blue one is because you sort of seal it after 37 days. The difference due to actually cracking already occurred here a little bit, and therefore the two spans are moving into different slightly ways. So I think then the question is, we got these behaviors here, how do you account them in design? So we got them already incorporated in the Australian composite code. And I will say, my suggestion will be, push it to more advanced analysis. So this, I think, is really where the way is to go to really push future designs, not just from a serviceability point of view for time effects, but also for durability, because the features you need to calibrate for the time effects are also those driving the durability issues. So in this case here, for example, I'm just going. So these are some comparisons of different tests than elsewhere, not by us. So again, you always have this trend where the experiment, has to be really meshed only when you got a shrinkage gradient. Without it, you're really underestimating deflections. And this applies to a lot of them. So this is just confirming again for different test results. And this is when you want to push it. Say, for example, here in a more complicated models, I call them multi-physics models. What I've done here, this is one way to approach this. It's quite a simpler model out of those that you can develop in this space. And what is the issue here? The issue is that I circle all the parameters you need to identify, material parameters. So the idea here is now that at least we've done some work where basically we're trying to optimize the test that you need to do in order to close, to basically identify the parameters. Because when you got so many parameters, you actually have different sets of parameters that actually will give you the right solution, or this solution you measure. So I would say the challenge is really there. And it's just to show you how, with this sort of multi-physics model, we were able to identify the parameters just for the concrete mix, and then actually we're able to capture quite well the response. So I would say this is where I would love, at least future trends in our stands, I will try to push them, to really move over the multi-physics heavily. And again, similar trend. And these are not sort of numbers that we fudge. So that's actually what's beautiful. It's actually parameters we identify through a particular process. Now, just a final remark, so we close very quickly, is I think what is worth going to advanced modeling? Well, okay, you can do it for fun, but I don't think it's actually very useful if you're actually talking to industry. I would say when actually serviceability state is governing the design, that's fantastic. And I would say one also you want to extend design life of structure. So there is a lot of examples now where buildings have been sort of maybe demolished only partly and then, sort of retrofitted, extended, and, for another, say, 50, 100 years. Now that the world is 100 years, the design life. So it's quite useful in the space. I think one thing which actually in engineering, we were talking earlier with Professor Novak, is that I think we need to have more information also on the buildings, how they behave. I mean, we are quite different from the industry where, if you sort of buy a car, you buy because it's beautiful, also because, the technical specs of the car. In buildings, usually you tend to only go for the view. You tend to go for, where is it? How big is it? How it can show off. You don't actually go with the specs of the building. That's where I think we have to educate also the customers, as you will have I would say, in a cuisine, in a restaurant. It's that level, I think, of evolution that really we need to also expand. And of course, if you then push these kind of models, you can use them for maintenance because now you go time effects, but also durability. And I think low carbon concrete's got a lot of issues with time effects. So actually, these models will allow you to really push them because it's variation in temperature and humidity have a big effect. And I would say also there is a trend in industry where really they're going into very, very fancy solutions. So just would like to recognize a lot of funding came from the Australian Research Council and also colleagues actually, we have been funding sort of playing through these models. Thank you very much for your time.
So thank you very much, Gianluca, for your huge presentation, a lot of information, a lot of content. We have 5 minutes, around 5 minutes for questions. Please. Left.
Good morning. I am Theta Rasmi from IIT Madras. Your work discusses approximation for the aging viscoelastic behavior. How this, it is sensitive to different creep parameter and the shrinkage strain parameter, because in the numerical approximation, what they do, they assume the time derivative of stress is neglected or it is assumed to be constant within a discrete time interval. But in reality, concrete follow this ACI or FIB codal provision. They don't follow the Prony series model. So how this method is sensitive to when we deal with?
Okay, I hope I understood the question. So I would say, first of all, what you find in codes are sort of codified, and they are sort of exercises of statistical exercises to match a large number of data. What I showed you before is really to push it a little bit further to say you really need to work with your concrete mix. That's where you're going to gain a lot of gains in serviceability in state design. Otherwise, you have a variability, plus or minus 20, 30% in your results first. What about the numerical? I would say, if I'm misunderstood, you're talking about the time stamping. That to me is something that you can check the convergence. So it's a question of how you build up your time stamping over time. That can be easily measured numerically. You can always create pseudo-experimental data to test those kind of performances.
Okay, thank you.
Thank you.
Yeah, so the question is, how important is advanced analysis for buildings versus bridges, let's say? In other words, how important these creep, shrinkage effects in regular buildings versus outdoor structures?
Yep. Well, it's I will say, at the moment we are tied by a legal system where basically always, if I'm talking to engineers, they always want to go to deem to confirm, deem to comply, provisions. What I showed you before is that, for example, the composite slabs with the sheeting, if you are just following the standard, you will actually miss out on the additional deflection. So for example, let's say you are designing that kind of scenario, then you will have more deflections, and the occupant of the building will complain that you go to court, and in court you will say, okay, you complied with the code, but actually the code didn't comply with what the slab wanted to do. In a way, we have to listen to the materials and the structure. So I will say, I find them very useful. I will flip the question around, is what is the cost not to try them? Because otherwise we always keep on thinking, it's like I'm saying, when you go to a restaurant, you're always curious to try something, you try, and then you see whether it was worth it. I think there is a big impact in the sense that sometimes you erect something and you have boundary conditions on ceiling that actually you think they're temporary, but actually if you stay for 30 days, they actually affect already the response, and you don't account for them. The advantage I'm pushing here is that once you concrete, at least in the approach I'm pushing, is that once you characterize your concrete mix, you can actually just use those parameters in any environment, because what drives then the modeling is actually your temperature, humidity of the environment. So it's actually, you're pushing to a level I would say, you know what, I will be more comfortable, because actually that's what it's about, more comfortable with this approach and actually some guess statistical results. So it's more about the future. It's more about, in 50 years time, when and the durability aspect comes in. So thank you.
Maybe one final question. Oh,
Very good morning to you all. Yeah. So creep is intensively stress dependent. I hope.
Sorry?
Creep is a
Stress dependent.
stress dependent.
Yeah.
At what intensity of the stress it is considered? That's my question, sir.
Sorry, what?
Creep is the intensity of the stress dependent.
No, it would be any stress level. Like it's like if I pull a polymer or something, like, it's whatever stress level we will build up creep. The question then is lower stress levels, you have a linear relationship like you saw before, what typically used in the code. At higher stress levels, you actually have to account for there's microcracking, they're more complicated behaviors. They're called no linear creep. So, thank you.
okay. Thank you very much.
Thank you very much. Appreciate it.
And thank you for the discussion. Now we continue, and it's really a pleasure for me to announce Professor Ravindra Gettu. Yesterday evening, we have identified that we already have met in '94. This is just a couple of years ago, but we didn't know each other. So but it was a very significant. It was a very no, wait. It was a very significant meeting. It was in Barcelona, and one of the PhD students of Professor Wallraven, he gave a lecture about non-applicability of the principle of superposition. And there was Professor Bazant, I think a lot of you, they know him, and he came into this room, and he also was in the room, and also me, and then he came to the room. I never accept what you are talking about to this PhD student, and then he left. And we both were sitting and we didn't know what to do. So it was a very impressive situation, but this is life, and this makes it interesting. So, so I'm very happy that you will be able to give a plenary talk today. And I think most of you know him already. And he is professor of civil engineering at IIT Madras, not far from here. And he was working as a president of RILEM and has made a lot of publications, a lot of contributions. And I'm very, very, very happy that we have him. And he's already on stage.
Thank you, Professor Novak. It's a pleasure to be here. I'm particularly happy to be at IIT Tirupati, and which is headed by a very good friend, Satyanarayan. So it's nice to follow Gianluca and to be sandwiched between Gianluca and Venkatesh, who will scare the hell out of you about fire. And I'm sure you won't sleep tonight. But I'll talk to you about something nicer with a cynical note, and talk to you about what I think structural engineers and most practitioners forget, which is the material, which is very important, the structural material. So I'll talk to you about it. I'll also pitch our center. Professor Satyanarayana is notionally part of our center on technologies for low carbon and lean construction. Some of you are aware of it. Very young group, I'm the oldest there. And our mission is to look at different aspects that are needed for taking a new material, an innovative material, into practice. And this cannot be done by just looking at the material itself. The design is important, how to construct is important, automation and so on. So we're trying. Obviously, it's a tough job. Ideally, we would like to see construction without any carbon footprint, with zero waste. It's a tall order, but it's an ideal that we think we should be striving for. So having said that, there are a lot of issues related to materials, related to new technologies that I'd like to touch upon. Cracking is a big problem. Everyone you talk to at sites would say that cracking is always occurring. It could be because of plastic shrinkage, thermal shrinkage, which often we don't know how to handle from the structural design point of view, or sometimes even from the construction point of view. Testing, where to test. Some people say, who is going to test, the RMC plant or at the site? And sometimes it falls between cracks. What age we should test, what frequency. Durability is and will be a big problem. We have corrosion happening. You will hear from my colleague Radhakrishna Pillai tomorrow. Leakages everywhere. There are buildings where having a bucket is very, very common in your office or bedroom because you don't know how to take care of the leakage. Then sustainability is something that we have to take care of. We are building like mad. We are using up raw material like crazy. And we are making mountains into ditches because we are taking away all the aggregates. So carbon footprint, raw material consumption is very, very important. And a big problem for a country like ours is water. See, when we teach about concrete, all of you who have studied concrete will remember that we say potable concrete, good quality water should be used for concrete, potable water should be used for concrete. But this is the water that you're taking away from people. So this is the paradox. People need houses, need bridges, but they need drinking water. Now, who has to sacrifice the water? Places like India are suffering, other parts of the world also. We're running out of water. There are disputes going to be there for water. Wars may be fought for water. But we are insisting that good quality water should be used in concrete. We should start looking for alternatives, and we are looking at treated sewage water. Let us mine sewage water for concrete. Let us not use drinking water. Let us think of how we can extract water that is not drinkable and use it for concrete. Then unconventional concretes, obviously, are a big thing. We have to keep looking at. This campus has a very nice example of fair face concrete. And this is not very common. A lot of effort goes into making concrete like this. It's easier to plaster the concrete. When often I ask people, why do you plaster concrete? The general answer is aesthetics, you get good finish. The real answer is we are covering up our mistakes. Otherwise, you don't need it. Why do you plaster a ceiling? When you make a wonderful concrete, you damage it by hacking it, and then you put this plaster and say, okay, now I have a wonderful structure. No, you just covered up your mistake. At IIT Madras, Satya knows this story. When we took the plastering away from the bill of quantities, the contractor offered to do it for free. Real story, real story. This what happened. So these are issues that we have to look at. Then other thing is precast concrete. So I'll touch upon certain things. We are talking about precast a lot. We think it's a solution, but there are problems. And these problems could arise because we are trying to do sustainable concrete. We are trying to do new materials. We're also going to do precast. And some of these things are causing issues. So let us imagine that I've come up with a new cement or new concrete, and I want to implement it at a site. Now, who are all the people who have to make decisions? Who are the stakeholders? Starting from the contractor, the constructor at the site is worried about workability, worried about how much super plasticizer I have to use. Can I pour the concrete fast, or will it delay the setting? What about plastic shrinkage? So this is the first stakeholder, important stakeholder who comes in when you're talking about new cement or new concrete. If they reject it, all your amazing stuff goes out through the window. The structural designer doesn't understand, please, all the structural engineers have to excuse me. They don't understand about plastic shrinkage. They don't understand about workability. Somehow they will get it done. It's not our problem. We are going to worry about strength, stiffness, shrinkage, and creep, right? But if the contractor throws away this concrete, the structural engineer has no chance of designing with this concrete. But for the user, does the user care whether you use the right amount of steel or you use M40 concrete or M30 concrete or not? The structure has to be durable for the user. I am living in some place, I want it to last as long as I want. Now the researcher comes in and has to do something. We have to make a living. So you try to connect all these things and come up with formulas and a lot of power equations and all that stuff to get this done. For the administration, suppose they want a new city or a bridge, they want service life. This depends on many of these other things from the beginning. You construct badly, you don't cure well, and your life suffers. So these are different things, and obviously the planet suffers if you don't do a good job. Your carbon footprint is gone. So what is unique about concrete, which is not there for any other material, is you have multiple stakeholders and anyone can stop you from implementing a new material, or be it structural or whatever. So this is the big challenge. And we have to try to understand all this. So at IIT Madras, what we have done is, when we take a new material, like we've worked on this new type of cement called LC3 for about 10, 12 years. Now it's been recently standardized. We will see it in the market soon. So we said we'll have to look at all these aspects. Otherwise, just doing a bit doesn't mean that you're going to help this concrete be implemented. Okay? So we have to see the first part, make sure that the contractor, the constructor, is comfortable with this concrete, not scared off because the super plasticizer demand goes up, plastic shrinkage happens, then they will just refuse to use such a concrete. The structural engineer needs also parameters and so on. So all these things are important. And also what we realize when we implement new technology is all of it is not wonderful. But researchers will only talk about wonderful things, because you cannot write a paper saying that all these things are wrong with my technology. All these things I've done wrong is never seen in a paper. You always say wonderful things. Now, we know that fly ash concrete or any concrete which has very little clinker is good for chlorides, bad for carbonation. We play it down. We say that carbonation will hardly occur. But we have to talk about these things. We have to understand the pros and cons, or somebody else will find out the con and say that this is a bad technology. So this is very, very important that we do everything needed to take something into practice. So, and we have to keep things simple. So we use this very simple test called the Marsh cone test. It's so simple that people said this will not work. And we had to do a lot of rheology, sophisticated tests to show that this works. So what this does is you take 1 liter of cement paste, pour it into the cone and measure the time taken for half a liter to go through. Then that's one of the points in that, and the curve on your right. And you can see that these curves shift. Ordinary Portland cement is below. That means it flows faster. It needs less time. LC3 less, and LC2, which is without the cement, is the limestone calcined clay, needs more time. So this already tells me that I'm going to have problems of workability. This means I have to put more super plasticizer or a different type of super plasticizer. Just in the paste level with 1 hour, I can get this result. So if we can do this more often and have tools that the user can use at the site, then makes things easier. So with this, now we know that if you're changing the type of cement, I have to change the super plasticizer, change the dosage. Don't try to do it with the same composition. It will not work. So these are things that we can look at. Now, adding on to what Gianluca said about the 2 types of shrinkage, I'm going to give you 3 more, because we start a little bit earlier. Plastic shrinkage is very fresh, concrete cracking. This in India is tremendous. We have huge problems. People will go for lunch and come back and the concrete is cracked. And who will they blame? The cement or the RMC? They forgot that they have to cure. When is curing usually done? After 24 hours. And if you cast concrete on Saturday, when do you cure? Monday. Concrete doesn't know this. Concrete doesn't know that Sunday is a holiday. It happily cracks. Reality, you go to sites, large slabs are cracking. Large slabs are cracking, and then people say, you made us use fly ash. Yes, fly ash will crack, but you have to cure earlier. You have to. So I tell people, simple thing, push your thumb into the concrete. If it doesn't go in, start curing. No need for any sophisticated maturity meter. Just use your thumb, and it works. Plastic shrinkage, autogenous shrinkage, Gianluca very nicely showed that this is going to become more and more important when you have higher grades of concrete. Similarly, thermal contraction. Diaphragm walls, very systematically, most diaphragm walls have a crack every 2.5, 3 meters. Professor Prasad, they come to him and say, cracking. He says, did you cure it? And they say, we will start doing it. So the first 3, we never studied about. When I was a student, we never studied about the first 3. Because you had so much water in your concrete, it did not crack due to the first 3. Drying shrinkage was important. Now you're putting so little water, you're putting 0.3 water cement ratio, 0.25 water cement ratio. The first 3 are becoming important. Drying shrinkage and carbonation, maybe not. The concrete will never undergo any drying shrinkage, but it will crack much, much earlier. So these are things we have to understand. When you change things, concrete changes. It's not the same concrete, but it's a different concrete and behaves differently. So one easy way that I tell students or even consultants to remember, when you see a crack, the first question you should ask is, when did you see the crack? There you get half your consultancy fee. If somebody says there's a crack, just ask when it happened. And most of the time, this resolves the issue. Yeah. So this is very, very important, very simple. And if we can take care of this, lot of problems will be resolved. So we started looking at what is going to happen when you have different types of cement. CM is the ordinary Portland cement, PPC is with fly ash, PSC with slag. You see that the crack width is increasing. How did we do it? We take a slab of concrete, freshly made, put it into this chamber and blast it with hot air. I think Dinakar sort of set this up when he was with us. Crack initiation time is becoming lesser. Cracks are starting earlier. That means you have to cure fly ash concrete, slag concrete, LC3 concrete earlier and cure for longer. This is very, very important. We cannot relax and say that, okay, the concrete is taking care of itself. It will crack. So this is very, very important. Look at the numbers on your right. And you can see the increase in crack area. So we actually measured how much the crack area changes under these circumstances. The fly ash content is 15-30%, GGBS is 15-30%. Crack increases a lot. The strength is the same, workability is the same. From the structural engineering point of view, it is the same concrete. But the material has changed and now it's going to crack. And this crack will stay forever in the structure. Now, what do we do about it? I'm not saying throw away fly ash and GGBS. Simple thing. Put 1 kilogram of polypropylene fibers into your concrete. Most of this cracking is resolved. Very simple cure. Very little cost. Very little effort. Nothing else changes. Can be done. So these are things we have to understand. And if you understand that, new technology can go in easier. So this is something we've seen even in newer concretes, 3D printing. We were involved in this post office construction in Bangalore, 3D printing. So that is me on the ladder looking for cracks. Yeah, this is one crack looking for many cracks. So this is what I do for a living. So I climb on this and see where are the cracks. And lot of plastic shrinkage cracking. 3D printing is prone to severe plastic shrinkage cracking because you don't have aggregates. You have thin elements, very high surface area, very high cement content. This on a hot day, little bit of evaporation is going to give you a lot of cracking. Otherwise, the project is wonderful. But you can have cracks. There is work happening in IIT Tirupati where they are looking at cracks. You can see the cracks. Whenever concrete curves, there is a crack. Again, from the mechanics, you can understand there is hoop stress and so on. But we have to look at it. So what we finally have to do is maybe in 3D printing, just behind your nozzle, there has to be a mist sprayer. Just like your nozzle is moving, there has to be a spray just behind, which will sort of keep the concrete wet. Otherwise, amazing technology will be thrown away. Your user will say, it's all cracked. I don't want a building like this. I don't want to live in a house like this, an office like this. But simple things can change, and we have to understand what happens. So let me move on to structural concrete. And durability becomes very, very important. Strength becomes important. Structural engineer has to design. They need to know the Young's modulus and so on. So I'll give you examples of some of the concretes that we have tested. First of all, strength. We should know that early age strength depends on the type of binder. The final strength may be the same. It may be M50, M40, but the early strength matters. Why does it matter? Because of deshuttering. Precast concrete. Now, when you talk to precast prefabrication companies, they almost rule out fly ash concrete and slag concrete. Even though you can pitch sustainability, talk about carbon footprint. Why? Because they want very early age strength, which we hardly study. Doesn't come into our structural codes at all. So what is the strength they want? Normally now in India, they are asking for 15 megapascal at 15 hours. Okay? It's practically impossible if you have 50% slag, 70% slag, 30% fly is practically impossible. So this is now negating the use of special concrete, special binders, blended binders in concrete. So we have to work on that. We have to see how to push up this strength and not worry only about the higher strength concrete. People looking for research ideas, we should look at early age strength, 1 day strength, 15 hours strength, 16 hours strength. That is where research should be put in. Then we have to look at Young's modulus, which is also important. So these are things we have to measure, not just use the code formula for finding out what is the Young's modulus, but we have to measure when we are looking at new types of concrete. Creep and shrinkage. Professor Ranzi very nicely talked about it. I won't get into it much, but shrinkage also can change. Because when you change the binder type, you will also change the binder amount because you want to match the strength. So this, what happens when you put more paste? More possibility of shrinkage, more possibility of creep. So these make subtle differences. And when does the shrinkage occur? Now, with a lot of tests with many concretes in India, we are finding out that shrinkage and creep stabilize in fly ash concrete after about 2-3 years, whereas it would stabilize maybe in 1 year in normal concrete. But where do you do tests? You don't have enough models. Okay, we don't have enough data. So this is something again that we have to start looking at. Again, about prefabrication, one thing that Professor Prasad and I have seen is when you do prefabrication, you want to remove your element from the mold and take it to site and install. How early? Maybe 3 days. Or your calculations have been done for 28 days. So once the concrete slab is in place, what continues to happen? It continues to shrink. If your joint has been closed, your joint will crack. The joint will open. So these are simple things. When you talk to a designer, they say, I've done it according to the code. But you have installed the element in 3 days, not at 28 days. Okay? So strength will pick up, but your shrinkage also will happen. So these are subtle things which dictate whether you can use a new material or not. Let's look at the benefits of some of these new concretes. Resistivity is on your y-axis, it's in the log scale. Resistivity, when it is higher, that means corrosion is slow, because corrosion is an electrochemical process. Radhakrishna will talk to you about it tomorrow. And we find that ordinary Portland cement is the worst. So if people believe that ordinary Portland cement is good for durability, it's not a good thing when you're talking about chloride. Very clearly, I'll show you this and I'll show you diffusivity. So again, diffusivity. We took concrete, put it in salt solution, and what diffuses in is faster when you just have ordinary Portland cement. Fly ash, slag, and so on will slow this down. That means your cover is protecting the concrete better. So there are a lot of good things that we can take advantage of. Diffusion, the black bar is ordinary Portland cement. Concrete is allowing chlorides to go in much faster than the blended binders. Okay, so for durability under chloride attack, very clear you get longer life with blended binders. Carbon footprint. We talk a lot about carbon footprint. There's hardly any data in India, Indian conditions. So we started going to cement companies, getting the data directly from plants, and you can see the benefit in Indian conditions of using blended cement. You bring it down from 900,000 kg of CO2 to about 500, 600 kg. So huge benefit. Without changing any other property. The cement complies with the standard, but it has a lower carbon footprint. Similarly with energy. Energy also comes down a lot. Your cost comes down a lot. Raw material consumption comes down a lot. Same thing with concrete. So that data was put into making concrete, and we also find that the carbon footprint comes down. Higher grade concrete is more effective. Higher grade concrete means that your carbon footprint of the building will come down. You will use less material more efficiently, so that way it is better. So if I have a choice between M50 or N30, 50 megapascal concrete at 30, 50 would be better because you will use less material and therefore overall consumption will come down. Now, question is, we can talk about sustainability, but at the site, how do I choose a sustainable concrete? Okay, so this is the question that people were asking us. All this is fine. You guys have done a lot of work. How do I know at the site which concrete to use? So we said that we look at these aspects which we felt were important. Strength, because you cannot sacrifice stability and safety. Workability, because you need it at the site. Embodied energy, because it talks about raw material usage and cost. Carbon footprint and durability. So we put these together in two indices. The first one is called energy intensity. So energy intensity is energy consumed for cubic meter divided by the compressive strength. And what we see is a nice trend. As compressive strength increases, this energy intensity drops and stabilizes. It also tells us that we just cannot keep on increasing strength. It doesn't really help. So this is my first parameter, energy intensity, which tells me about the embodied energy and indirectly the cost as well. The other one, what we call an apathy index. Apathy index is your carbon footprint divided by a service life parameter. So why do we call it apathy index? Because at the site, nobody cares about these two parameters. Nobody cares about carbon footprint. Nobody cares about durability. They want to finish the project. Defect liability period is 1 year and they want to get out. Yeah. So we want to decrease this, obviously. So suppose you have chloride attack. This is what the equation looks like. So you have carbon footprint at the top and below you have diffusion base factor. So what do we do? At the site, if you're only looking at 28 days strength and workability, there are actually infinite compositions of concrete that will fit in. Infinite compositions of concrete can give you the same workability and same strength. Now, let us take as many as possible that you can do and do this plot. On the x-axis, I have energy intensity. I want to keep it very low. Apathy, I want to keep it very low. And when I compare, some of these concretes really turn out. Of the concretes we've studied here, now LC3 comes out well under chloride attack and so on. We can do this for more. So we went and did 30 concretes, different concretes. And again, you can choose which ones are at the left corner and this comes out better. So this is easy to do. Not a lot of calculations, but go to a catalog and do this plot for your concrete at the site and you can choose what is sustainable. Now, this is not all talk. Actually, this was done. So this bridge in Kerala, again, Professor Radhakrishna Pillai might talk about it. The middle span, we were allowed to change the mix. The outer spans were designed for M40 concrete. So we took the chart on the right that I talked about. The upper pink points and pink and orange points are the spans on the extreme, normal concrete that they were doing it. Middle span, they allowed us to change the concrete. This is because my colleague Radhakrishna Pillai has an immense convincing power. He pains the hell out of people so that they agree to whatever he says. So they allowed him to change the span. Real bridge standing. And what could happen is they went for 70% GGBS, same strength, same workability. Life expectancy for corrosion to initiate went up from 30 to 125 years. Carbon footprint saved just in one span 800 tons of CO2. Okay, so it can happen. But what is very important is to get to this point. Not just stay in the lab or on a sheet of paper and say, I have saved the world. You have to show and you have to convince people. So to conclude, I would say that if we are talking about sustainability, if we want to make a major change in sustainable construction, these are some of the things we have to work on. There is no other option. We have to look at low carbon cements, better construction, better durability, and so on. So with that, I'll stop. Thank you very much.
Ravindra, thank you very much for the very nice talk. And you have made, I would say, several very impressive statements. And curing is one of the most important actions after casting the concrete. Sure. And what I also would like to say is you are burning for your profession. And this is perfect. I like it. Thank you. So now we have 4 minutes for discussion.
Good morning, sir.
Morning.
Very interesting and implementable ideas that you have given.
Thank you.
Just a test on that surface resistivity test.
Yes.
How effective it is, sir, in terms of measuring durability? Because there are so many other tests on durability of
Right.
concrete.
Right. Considering the ease of doing the test, I think it's very effective. We have done a lot of correlations between surface resistivity and diffusion. It works very well. It works very well. Now I think it's come to a point that we can implement at site also very easily. The Venner probe used to be very expensive. Now there are Indian-made models which are going to decrease the cost by almost 80%. So it will also be not an expensive meter to buy. So I think I would bet on it. Yes,
Ravindra, excellent presentation.
thanks.
I'm not going to ask you a fire question.
Well, you deal with fire.
But one question is, why is it not in the codes and standards, strict regulations or something? We know that by adding this fly ash and other things, the cracking starts at 12 hours, you said 16 hours or something. Why is it not still mandatory regulations are in codes, especially when countries like India, where everything is for fly ash and other things extensively used?
Venkatesh, good question. I think because some of the things we don't know where to put it in. Because sort of IS 456 starts when the concrete is already hardened. This is happening before. So a lot of construction manuals have it, but it's not a codal practice. See, we don't pay for curing. Why should somebody do it for free? So I remember Pierre-Claude Aitzin, you know him, used to say, put an item and pay for curing. Now, who does curing at any site? Somebody who's loitering around, supervisor comes and says, go wet the concrete. This is what happens, at least in India. But we don't pay for concrete. Why can't we put a bill of quantity item, say curing, and have one person just for curing? So these are things we have to do. It's sort of implied that it's a good construction practice, but we don't do it. Nobody pays for it and it's not stipulated. Yeah. So I think very right. It should somehow be made mandatory instead of a recommended practice or a best practice. I agree. Yeah.
You have said about the indices, sir. How much that is possible for, at least for Indian standards, to implement those indices in our codes? Means how much time it will take for the, because, and what will be the standard range for those indices? That we have to decide. Otherwise, the things will
No, I think we are far from mandating something. What I'm using it only to compare. I have multiple concretes. I can see which is better. I am not going to go to the extent that it should be so much. I think it's a bad idea to do it today with the information we have. But if I have 10 concretes, I can tell you which is better or which is the best that I have. That is as far as I want to go for now.
Thank you, Professor, for your wonderful lecture. So in terms of concrete, mostly we speak about SEM and alternate binder. But as you mentioned in your first slide, like water is the one of the important aspects. So if you wanted to use water, the wastewater, what are the aspects we should look for? And even for concrete curing also, we are using fresh water. So can these both things to be done separately, like for use in concrete as well as for the other purposes when we are making concrete?
Yeah. Thank you. I think it's a good question. We started working with a company called Lafarge. Unfortunately, they closed shop and left India. So, but what was interesting is the concrete turned out to be better when we used treated sewage water than the groundwater that was being used in the RMC plants. Because what is happening in most big cities is we are running out of good water and we are using brackish water. So treated sewage water can actually give you better quality concrete than the groundwater that many plants are using. Yeah. So we are reviving. We started doing some work. Now we are reviving it. We see that there's a lot of interest globally. Even places like California don't have water. So this is not just an Indian problem. Many countries are facing an issue with water, and I think we should work on it. Yeah.
Sir, can we get some guidelines when how much time after we have to cure and all that for a different fly ash percentage and
They're very simple. You have an excellent equipment in your hand. I use my thumb. I push. When it doesn't go in, I start curing. Yeah. Let me not give you formulas and codes. Just tell your site guy, go push your thumb into concrete. Doesn't go in, start curing. Very simple. It works. Nobody has ever told me that that's failed.
yes, yes.
Yeah. Otherwise, sir, if I give you a formula, then that will not work in Tirupati or Chennai or Delhi.
Okay.
Then they will say, okay, Gettu's formula is wrong.
Yes.
Yeah.
Okay.
It varies a lot. Depends on your evaporation rate, depends on starting temperature, lot of things. So I think let's not look at formulas.
Okay.
Very easy. Observation at site. Somebody is going to be there anyway. Let them do it.
Okay. Thank you.
So this was the this was the final question because we're running out of time. Sorry,
Okay.
but maybe
I'll be around during tea break.
you know there's high tea half an hour. Then you can talk to him 25 minutes, and then you have 5 minutes left for his tea. Okay. And thanks again for this very impressive talk and for the discussion. And a big applause for him again. And now I hand over the microphone to the anchor woman.
Thank you, Professor Gettu, for the presentation. Now we have special presentations from our platinum speakers. First, by the Ramco Cements Limited and Ramco Industries Limited. As a leading name in the construction materials sector, Ramco has consistently driven innovation and quality across the industry. We are pleased to invite their representative to share insights into their ongoing work and contributions to the field of structural engineering. May I invite Platinum Speaker Mr. Anil Kumar Pillai, Senior General Manager of Technical Services, the Ramco Cements Limited and Ramco Industries Limited, to give his presentation on the topic Ramco Construction Chemicals and Overview.
Yeah. Good morning and very nice to be here. Thanks to IIT Tirupati for having given us this opportunity to be part of this conference. As you all would be knowing that Ramco Cements has been synonymous with cement, but then we had a dry mix plant way back in 2002 at Sri Perambudur, where we were manufacturing mostly tile fix products as well as putty. And we had also developed various types of plasters, especially the spray plaster and various kind of composition as plastering is concerned way back in 2002. And then now we have continued and we have brought in various kinds of construction products, which would be a solution for the construction industry. So I have been given 10 minutes, so I will try to confine within the 10 minutes itself. So this is what we have got. So we have got, as well as, just let me go to the next slide and just give you a brief. This is what we have got. Tile laying products. We have got tile fixes, both cementitious as well as epoxy, as well as in tile grouts, we have got again cementitious and epoxy tile grouts. Then we have got, as far as plasters are concerned, we have been developing various kinds of compositions as far as plaster is concerned. To begin with, we had the ready mix plaster, wherein you don't have to mix sand, you just need to add water. Then later we developed self-curing ready mix plaster, where you don't need curing. But then what happened was that there was a problem of changing the mix proportion. So we have brought in a product which is called a self-curing cementitious product, where you can add sand into that and then you don't need curing. So that is what we have been evolving the product as well as self-curing plaster is concerned. We have block fix, wherein you have a special adhesive to unite the AAC blocks. But then for other block, like, hollow blocks, solid blocks, we are in the process of developing product for that also, so that, it can be pasted effectively. Then superfine, of course, is a putty. Waterproofing products, we have the integral waterproofing compound as well as the brush coating, the what you call a kind of membrane which is there. So we have got two products as far as waterproofing products. We are in the process of developing many more products in the waterproofing area. Bonding agents, of course, to unite the old concrete and new concrete, we have got SBR as well as epoxy. And for repair products, we have developed both micro concrete as well as what you call the high strength grout. So this is a brief overview of the products that we have got, and we are in the process of bringing in more products. Just to give you an idea, because most of you are students, I'm sure that you would be interested in to know what are the kind of tests that we do on this product. As far as tile fix is concerned, there is an IS code 15477, which recommends various types of tile fixes based on the size and the type of tiles. So we have from type 1 to type 5 as given in the IS code, and we have the corresponding Ramco range of products. It is there. The one development that we have done recently is that there has been a kind of demand for epoxy tile fixes because of the kind of adhesion that is required, and they don't want to take much risk as far as the tiles are concerned. So we have developed that. So the kind of test that we do, these are the test of interest is the deformability test. The basic test that we do is tensile adhesion and the shear adhesion strength as well as the tile fix is concerned. So these are the kind of tests that we do. The slip test, of course, as compared to cement mortar, it is always advisable to go in for tile fix because of the inherent disadvantages as far as that cement mortar is concerned, because it shrinks, you cannot do curing. But as far as this tile fix is concerned, it is a self-curing product itself. So tile grout, of course, we have this, and it has been a kind of problem for many of the users as far as the grout is concerned. So we have developed a epoxy tile grout so that it fills the gap between the tiles and gives a much more effective this thing, and it is also chemically resistant. Wherever acids or chemical products are being used, you can go for epoxy tile grouts. These are the kind of tests that we do: water absorption, degree of whiteness, consistency, chemical resistance test, again tensile adhesion strength, because by the nature of the product itself, you need to look at that. Superfine putty, again a common product that is available in the market, and we have this for a number of years. So tensile adhesion strength is one strength that we do, the test that we do for this. Setting time, pull-out strength, because pull-out strength test, you will see that it is a common test for most of the products, because being a thin membrane, you got to do that pull-out strength for most of these products. So we have that. Spectrophotometer test is one test which tests the degree of whiteness of putty itself. So that is block fix. Of course, we have got the critical test that we do on that is the split tensile strength. Where it fails when you have that paste and when you use it, at what load it fails. So that is what the split tensile strength that we do for the block fix, and the tensile adhesion strength again. Super shield, of course, the integral waterproofing compound which is added to concrete. The basic purpose is to reduce the water cement ratio. It is basically used in the retail segment where they are not able to reduce the water cement ratio by using the conventional this thing. So it affects in reducing the water cement ratio to such an extent that your workability is not compromised and you get a higher strength, and thereby the durability is also enhanced. So these are the kind of tests that we do. Water permeability test is one test that we do on that as far as the integral waterproofing compound is concerned. Then the super bond and epoxy, both, of course, the primary objective of using this is old concrete with new concrete, but SBR is also being used as a repair mortar, as a mix of that. So for such applications also it is being used. So the kind of test that we do for that, elasticity, pull-out strength, again, for the epoxy bonding agent, tile adhesion strength, compression strength, rebar pull-out test, slant shear test. So kind of test that we do for SBR and epoxy. Again, this is, of course, we had compared with various products available in the market. That's how we, try to see how we can make a, the USP in our product. So we have done a detailed study at our research center, the Ramco Research Development Center, which is at Chennai, and we have done a lot of studies on cement, concrete, and various other construction products. So we have collected various samples from the market. We have done a comparative study, and we have seen which is the right kind of test, based on the feedback from consultants as well as from various experts in the market. So we have been able to do that. This is the aqua shield test, that is, the brush kind of coating that we have done. Water penetration test we have done, elongation test again. Food grade test also we have obtained for that product, because that is being most important, because many of the places they use it for water tanks and other places. So these are the kind of products we have got. Ramco micro concrete, of course, we have got in 3 variants: M40, M60, and M80. And these are the tests that we do on that: compression, flexure strength, and yield of that, this thing, flow, all these tests that we do. Super grout, of course, it is again a 25 kg bag, flexural strength and compressive strength. And most of this product, you see, what we have done is that before bringing into the market, we have used it in our own cement plant. Be it our silos itself, waterproofing compound we have used. The primary objective of our this thing was to use in-house. Over the last 3-4 years, we have been using in our own cement plant, and then later on what had happened was that we thought of why not commercially bring it out, most of this product. So as a challenge to various construction problems, most of you would have construction problems when you go to sites. There would be various challenges. So in answer to that, within our in-house construction, we have been able to develop from our various Ramco cement plants, and we have been able to develop these products. So this is what the super grout is all about. The kind of test that we do for that. Of course, dynamic loading test is one challenging test that is being done, but we have taken help from IIT Madras also for helping us to do the kind of test on this, because that becomes critical in many of the applications. So we would be, further developing the product based on the test that we, the results that we get. This is what the super plaster which I was talking about, the super plaster eco. Primarily, if you look at the construction side, the same cement has been used for plastering. It's surprising to see that even OPC 53 is nowadays being used for mortar as well as plastering applications, even in city like Bangalore, where we think that a lot of knowledge is there as far as the practical application is concerned. But there also you will find, I was surprised to see, and even 53 grade is also being used for fixing tiles, which is quite surprising. The answer to that is, many of them say that we have purchased some cement for concreting, so the balance cement has been there. So we think of using it for various other applications. But then the concept of right product for right application doesn't fit in there. So this is what the water retentivity test we do, as well as the air content, which is of course very specific to plaster. When you measure water retentivity test and air content, you will be able to understand whether the mortar is able to spread out easily, and whether it is having that self-curing properties or not. So we add some polymers for getting that self-curing properties as far as this is concerned. So thanks for your attention. Thank you so much. So my colleague from Ramco Industries also would give a presentation on the 10 minutes presentation. So I'm sure that this conference would throw a lot of light as well as the various challenges is concerned, and very interesting. I was fortunate to attend the discussion on concrete by Professor Gettu. It's always an honor to be there in this lecture. And of course, I also recognize the presence of Dr. Dinakar Pasla, who has been there from IIT Bhubaneswar, and we have also been doing a lot of works together. Thank you. And thank you, sir, Dr. Satyanarayana, for having given us this opportunity to being here and to interact with you. So as students, you can always come to our research center, which is at Chennai, not very far from here. And, we have a lot of studies that are being conducted. So if you want to have some kind of interaction with us, we would be too happy for that. Thank you so much.
Thank you, Mr. Pillai. Now we have our second platinum speaker, Mr. Janaki Raman, General Manager, Smart Build, the Ramco Cements Limited and Ramco Industries Limited, to give his presentation on the topic Sustainable Products in Construction Industry.
Happy to be here to present on behalf of Ramco Industries Limited. As you all know that we are consuming 30%, more than 30% of energy in the building constructions. So the more sustainable building constructions, if we have, the more better future we can build. Of course, as Professor Ravindra Gittu sir is quoted here, the sustainability and the water scarcity is going to be the major role in future. Yes, we have coming up with the new system, like we are pioneering in green dry constructions using our product. These are the basic problem we have during the constructions. We don't get timbers, we don't get sand. We have a lot of problems in the getting raw materials to do the building constructions. So construction is green, is what we say. Using your product, we can say around 98% water savings, and more lighter, 4 times lighter than the normal constructions, and excellent insulation property enhancing HVAC efficiency. And of course, using these products, we can reduce a lot of pollutions comparing to the conventional method of constructions. Yeah. This is our premium product, Hilex. It's a calcium silicate board, we call it. It has a different varieties in terms of acoustic tiles and ceiling tiles, design tiles. What is the major in this product actually? See, we have a 4-hour fire-rated systems and 2-hour fire-rated systems, mainly being used for the industrial projects and many of the institution projects and many of the major projects. In terms of using the conventional method, they prefer go with the 4-hour fire-rated partition system and as well as the 2-hour fire-rated partition systems. And water resistance, these are the major, we face the problem in the construction industry. When you use the product, will it be water resistant? Yes. Even if you soak a product into to the water in 24 hours, it won't break. It will absorb water, and this will get dried off after sometimes. And again, one more thread: will this product, termite issues will occur? And no, we say is a zero termite issues. And then the next, fungus. During the process of dampness or any kind of water into this product, is there any fungus? This will never allow microbiological growth into the product. And this is the best sound insulations which we have tested across the national laboratories. And this will give around 42 to 65 dB level NRCs, 0.7 to 0.85. And of course, when we use this product into the buildings, we have a problem normally, the impact issues. So it is the best product where this will give you 900 J per square m. And what we do using these products, these are the product which we have come up with the market. And by keeping this, what we can do, so we do the partitions, we have our own design system, design team, and we do designs according to the requirements, and we give presentation to the clients and see how we can fit our product into their requirement. These are the false ceiling systems and 60-minute fire-rated false ceiling systems. This is basically we get the drawings, design drawings from the architect or consultants. We prepare ourselves with reference to the drawings from the consultants, and we also go along with the RCP, that is reflected ceiling plan. Go along with the servicing lines, all MEP and all other services. And of course, without that, we can't design our false ceilings. And then the structural encasings, 120-minute fire-rated systems. And we also come up with a new product, which is high-density board, fiber cement boards, which is can be used externally for the buildings in terms of cladding, in terms of external wall partition also. Is basically high density superior strength of exterior product, which presently picking up in the market. As I said earlier, this product also has some fire resistant and wind resistant, water resistance, and then low thermal and sound resistant, eco-friendly. Another product we are coming up with ICCMS designer board, which can be used externally and can be used for the cladding and elevation purpose. And these are the other designer tiles which we are coming up with that in the market. Where we can use our product into the building, and this is a design which we made, and we can use it outer and internal false ceiling, even in the compound wall, even in the gates. So we have described where we can use our product into the different applications in the buildings. Of course, we are also coming up with the product like ILEX XFR, highly fire-rated partition boards. These are the ILEX XFR applications. And one more product we are coming up with presently market like ultra lightweight ceiling light. It is a Hilex light material. Again, this has the same thing, like we are different pattern. We are coming up with the design with NRC levels, and this also has a fire resistant and sound insulations, thermal low thermal conductivity, and it's a basically lightweight project. This is a technical specification of the product. One more product is green core. Is a roofing sheet. Yeah. What we do using this product is smart build. What we do in smart build using this product. So we do projects in terms of taking up the entire work and do this. And we do the technical consultancy in terms of the contractor or the builder or the owner wants to do with his own applicators. We do the technical consultancies and a continuous training to the people who are doing the work and the quality assurance. These are the range of projects we have done internally. It's a dormitory at Rajapalayam with LGS of construction. Another project in IIT Hyderabad, where we have done the partition walls as well as the ceiling, false ceilings. This is a project in Manipal University in Manipal. Here the challenge is that with the client, they want to do the terrace floor extensions with the lightweight structures. So we have proposed and they are agreed, and the project is completed live. And one more project, fire rated partition in Tata project in Chennai. Another project, other view of this, and the college, medical college in Bihar. As Professor Sir Ravindra Gattu sir quoted, the precast is a precast structure. The framed structure is the precast, and all internal and external is the partitions with our boards. Now more than 3 years is over. There is no issues. Another project. These are the fire certification we obtained it, and some of the product quality certifications we obtained, and green certified. Our product is a green certified, and it has been tested as national wise. And our product has been already mentioned in the various government visuals. And we are also in the cements, and as Anisa told, and textiles and other products. We are mainly exporting 50 to 52 countries of product across. These are our clients. Thank you. Yeah.
Thank you to our platinum sponsors, Ramco Cements Limited and Ramco Industries Limited, for the presentation. Now we will proceed for a short 30-minute tea break. And I request you all to reassemble to the same classroom as we continue with the remaining sessions. We'll resume the session shortly. Kindly be seated. Welcome back, everyone. We now continue with the next set of expert talks. I invite our plenary chair, Professor Novak, to take the lead and guide us through the upcoming presentations.
So hello again, everybody. For me, it's a real pleasure to introduce my colleague Venkatesh Kudu to his plenary talk. And maybe you don't know it, but I was several years heavily involved with temperature, but thermal actions induced by climate. And that means issue, but very interesting. And your title, which is titled Development of Ultra High Performance Concrete for Fire Resistant Applications. This is really a challenge because there are two opposite issues which have to be matched. And but before you start with your presentation, I just would like to say a few words about his position. He is professor at the Michigan State University in US, and I would say he is a real big authority and an expert in fire resistance design of concrete structures, I think mainly. And I don't know whether you know Kang Hai Tang from NTU. Yes, he's also a very good colleague, a well-known colleague of mine, and he's also very good. So I think you both are matching very good together. And he has did a lot of significant work publications with regard to fire resistance. So please come onto the stage and give your presentation. And 5 minutes before the presentation stops, then I make this, and then 2 minutes this, and then this. If I look at you. Yes. Yep. Please do.
Can you keep these phones there? I give it to Subramaniam. Here, yeah. This also. Good morning, everyone. Okay. First of all, it's a great pleasure and honor to be part of this, esteemed conference, right? Professor Balakrishnan, Bijali, we call her. She has done a wonderful job, and a group of volunteers as well, right? So I'm very pleased to be here in front of you to talk about development of ultra high performance concrete for fire resistance applications. Now, in this presentation itself, first, I'm going to give you some background to UHPC, which I am not an expert. There are a lot of experts sitting in front of me. But why fire is important, not only for UHPC, for anywhere when you want to design, we don't design in an engineered way today. So what's the problem and how we do it today, our designs for fire, and how bad it is, our current designs are. I'm going to show you that. Then I'm going to talk about performance problems. It's not just UHPC, even any high strength concrete, fly ash concrete, that garbage concrete, you throw in garbage and make the concrete. Any of them, when it comes to fire, what the problem with that is, I will show you that. Then some of our recent studies, including some of the innovative strategies, simple strategies you can incorporate to overcome this problem. You can engineer it. Codes doesn't say that today. Hopefully tomorrow they will say that, right? And design recommendations. Now, emerging trend, as you all know, in the construction sector is sustainability, performance, including durability and cost. And more importantly, carbon emissions is another major thing in some countries around the world. Now, UHPC is a recent material. Basically, it's It's designed for achieving high material performance. Its composition, you can make it with coarse aggregate if you want, but many times without coarse aggregate, you add fibers, low water cement ratio, right? This what's a lot of admixtures you throw in to make workability and other things. When you do this, its characteristics, very high packing density, as you know, compared to your conventional concretes, low porosity and permeability, and you get very ductile response if you add those steel fibers, right? Strength is higher. This is, you see this regular concrete here. If you add steel fibers, your strengths are much lower here, but it's ductile. But with UHPC, you can get much higher strengths and ductility, which whatever you need. A lot of advantages. It's not just the strength, but there are durability consideration. It's one of the best. It has been used not now for the last 20, 30 years in real applications, bridges, buildings, first started mostly in Japan, Korea, moved, Europe as well. Then it moved most recently in US, in fact, right? And Canada was much before that. We had a lot of projects which you can see on the internet if you want on all these projects. Now, it's structurally, when you use this material, you have a lot of advantages. High flexural capacity, reduce shear, increase shear capacity, cross section will be much less, but right, and even maintenance costs will be less because no corrosion and other issues. But when it comes to problems, right, brittleness you can overcome with UHF fibers. Another problem can be fire, and fire is very important. Why? Because if you look at the magnitude of the fire problem, you will see how important. Fires cause thousands of deaths and billions of dollars of damage in each and every country around the world. Remember, earthquake may not be a problem somewhere else, but still we do so much for earthquake design only in some regions. But fire, it's not like this. A small village to, to a town in Chile, it's problem. Now, when fire happens, it's a severe hazard and threat to the people, first responders, as well as our structures, built environment. Now, in US data, according to 2023, 1.4 million fires. There are a lot of fires which happen in the US, leading to 3,670 deaths, nearly $50 billion of damage. Now, when fires occur, they represent the most severe conditions that a structure can see. Temperatures go up to 1,000 degrees, not 550, 60, 70, 80 degrees centigrade, 1,000 degrees centigrade or more. And it can happen from an electric short circuit, as simple as that, which is common cause in India most of the time, or as a secondary event. After most earthquakes, you have followed by the fire, like Kobe earthquake, for example, New Zealand, and Chile earthquake. These are some of the recent earthquakes. It's followed by the fire, or a blast leads to the fire. An impact, a truck hits a bridge. Impact is nothing. That bridge is designed for the piers and abutments for impact, but you never design for the fire. Including in 9/11, as you can see that 40 buildings collapsed or damaged, not just 2 towers. 9 buildings collapsed. These are 30, 40, 70-story buildings. Much of the damage is because of the fire, right? But what was the primary loading? Impact. The towers were designed to impact loading, but not for the fire which followed it, right? So fire is a significant effect. Now, we put in, it's impossible to prevent all fires. So we put in a lot of measures. Building codes require you to put all these measures, including sprinklers, heat detectors. Look at the sprinklers there. Heat detectors, smoke detectors, exit paths, staircases for people to get out, firefighting to happen, firefighters to come and fight the fire. And the last one, in fact, which is much more important in Indian conditions, is structural fire safety. That's the one which will save lives. That's the one where property is saved, because in India, for firefighters to come, there is India, everywhere its own problems, right? And active systems don't work in India many times. And even in US, for example, there was no water in Los Angeles fires. Enough water is not there. So, and those sensors, they are very cheap sensors. You cannot, because of the cost. So those sensors may not work many times. which is common. So structural fire safety is one of the important things which you can do at 1/100th the cost of your sprinklers if you properly plan it. Those sprinklers are much more expensive to maintain and to build. So fire resistance is very important. For example, in 9/11 buildings, what we learned was, it was the most fortunate day. Unfortunately, 3,000 people died. But from the point of view of if those attacks were hit in the afternoon, and if it was a day of a hurricane or a cyclone, which is very common in New York City, the buildings would have collapsed in minutes, not in 60 minutes and 190 minutes, because the structure was designed to withstand 120 miles, but it was 7 miles an hour was the wind speed. So there was some resistance to withstand the fire effects. So fires can lead into significant damage and destruction. Higher the fire resistance, higher the resiliency of the structure. When you look at India, it is much worse, the fire problem. One of the worst records India has, 23,000 plus people die on an average in a year, based on the 5-year average statistics published by Geneva Statistical Institute. Even though India has significant population, if you look at it, it's still high, 1.7 people die per 100,000 population. Now, it's not just statistics. It's really happening. If you see that in Los Angeles wildfires, this is an eye-opener for US. In fact, immediately NSF opened up big fire grants because of that. So far, they were resisting funding fire, right? Because they realized, the government realized that damage is too much. 12,000 houses were incinerated, or structures, for example, in that region, right? And then same thing happened a year before in Hawaii wildfires, right? So it keeps on going. These wildfires are a new phenomena, and you can see that it is not, okay, let me first talk about India. India as well, number of fires are happening. In almost a weekly, you have a major fire happening. Yesterday or day before, Delhi, a chemical factory, I think it was on the news. Now, some Hyderabad, for example, the Charminar fire, very significant number of people died, 17 dead. Just before that, Kolkata, the hotel fire. And in some parts of India, like we are trying to do some project, where is Professor from IT Bhubaneswar. So we are trying to do a project. Oh, okay. So in this, hospital fires are becoming very predominant in India a number of times, right? So, so these fire problems, depending on the region, it's lot of societal conditions as well, or societal levels. It causes a lot of things, okay? Now, when it comes to buildings, I showed you, you can argue that UHPC most of the time is used in bridges and stuff. Recently, bridge fires are becoming much more common in the US, unfortunately. And you see number of bridge fires. These are, I'm talking about most critical bridges or most critical highways. For example, for those of you who were in the US, the bridge I-95, there were 2 times in the same highway. It has to be closed down for weeks, just like Delhi, Kolkata, or Delhi, Bombay. Within months, we had another major fire on I-10, which I'm going to show you here, right? This is outside of Los Angeles. And how the bridge fires happen, either an oil tanker hits the abutment or a pier. You design so much detailing, you put that for structural design, for earthquake, for wind, for blast. And some universities now teaching how to design for meteors hitting the earth, and somewhere else tsunamis. But we forget about this 4-letter word called fire completely. And we don't even treat it as an hazard. So in this case, right? So what happened was, and these days, US is bankrupt almost. And they passed another law to make it quicker bankruptcy just yesterday or last night. So anyways, in this case, what is happening here, as you can see here, so whenever there is a space like this, this is underneath, this is I-10 bridge outside of Los Angeles going from San Diego to Seattle. They rented it out. They rented out the space for storing old cars, which to take out the parts, and also to store wooden pellets. We have Home Depot and stuff. They rented space so that, and a homeless person comes in, just it costs 2 cents. He lights, I don't know, then after that they called him mentally disturbed or something. So they just put in a matchbox, he opens it up. And by the time the fire department comes in, look, can you see the spalling in the column? I will just later quickly show you, whole about 80 columns and the spans were completely destroyed within no time. Fires cannot be fought. Remember, this is the problem with the new concrete, which I'm going to show. Even their firefighters are afraid of touching your new concretes when you don't make solutions. So the bridge, the highway had to be closed. It's just before, one day before Thanksgiving. For us, Thanksgiving is just like your Diwali, where everyone travels. So it becomes a major issue from, from the point of view of transportation. So what do we do currently? We do a lot of things currently. It's not that we don't do. Building codes really have put in a lot of measures to overcome this. As I already mentioned, I will go to the next slide and show you. So if the fire were to happen, right, we need to put in so-called active systems, firefighting, and passive systems as well. What are active systems? This is how a typical fire grows in a building. You can see an ignition happens, fire significantly grows, then it becomes exponential, okay, this red line. And then after certain time, either the fuel runs out, oxygen runs out. So then it cools down. So first of all, we design for this fire, the green line. All building codes design for certain kind of a time temperature curve, which can happen in this building, which was applicable in 1990. 1919, not 1990. For 100 years, we are struggling to change it. I was in a lot of committees, right? Oh my God, I think it's easy to pass a bill in the parliament or the US Congress than in the code committees, right? Believe me, I mean, you might think that, it's easy to pass, to get an approval. So still they changed almost, and they came back to the same thing. So there is so much lobby. Now, so when this fire grows, so first of all, this is the curve we use, the green line. You might say that, it doesn't capture the faster rise in temperature. That's what the problem is. The second thing, as you show, as soon as this fire happens, we keep handheld extinguishers in the US. You can fight the fire yourself. If not, sprinklers has to come in. After that, smoke detectors has to come in. After that, you need a compartmentation. That's when the structure really sees the pinching effect of the fire only here. First, the walls, floors, your columns and beams will see the effect. So this is passive fire protection systems. They don't need any sensors, anything. Active systems, all this needs some evacuation happens here. All this needs sensors. And firefighters has to come in here to have a better chance. I mean, they can come anytime. If they want to fight the fire, smaller it is, easier it is. When the fire is in one room, no big deal. It's piece of cake. 2 rooms, no problem. But half the floor spreads, little bit danger. Whole floor spreads, much more danger. If it is 2 floors, before, firefighters used to break the walls and enter the building. We call it, there is 2 things for fire safety, pre-9/11, post-9/11. Pre-9/11, they would jump to save a cat, a dog, or anything. Your purse is left. If you tell the firefighter, he will go and get it. But now, they will try to move away as soon as, I tell them not to go into this building. This is a problem from life safety point of view, right? Big problem. Now, so fire is a major requirement. How do we do it? When it comes to structural systems, concrete structures, one thing I want you to know, when I talk about UHPC, I don't want to upset my colleagues here who are sitting. They're all UHPC or concrete experts. This is for concrete. I can say the same thing for new steels. I can say much more bad things about wood, FRP. Newer the material, my philosophy is worse is the fire. You need to do something to make, you need to engineer it. You cannot use 1919 methods or 1960s rules for that. So if you see here, what do? We put in, only things we do is, this is rebars, cover thickness, and the minimum dimension of a column or a beam. That's all current codes do in India, abroad, everywhere, okay? And what was the difference? I will show you. older structures which were built in 60s, 70s, 80s, you had huge mass. Now you are trying to slimming down. Everyone wants to be models, including our beams, columns. We want to design these shapes. So when you want to do this, right, you think the performance is good? No, the performance won't be that good. So this is Indian code. I mean, not different from other codes very much. And this code, how it was developed. It was basically, this code was developed based on 1960, somewhere one test was done. Still, this is how fire ratings are developed. One test on a structural element, they go to the lab. It's not even done in a university. There is no third party review. So they submit it and they get a, if you have, for example, for a beam, if you need 1 hour rating in a concrete beam, you know, that's the minimum dimension and cover thickness. That's it. Now, this is not good because our modern practices are different, lifestyles are different, our modern structures are different, our modern materials are. They were okay for 19. Much of this is taken from there. Now, if you see here, for example, the fire curve I already explained to you. If you have electric vehicle, in US, every house now has electric charging in their basements. If the basement fire starts, electric fire is entirely different. What you releases, it releases oxygen, some of these batteries, so it fuels the fire, right? Our bridge fire is different, right? So from this point of view, you cannot apply, and it doesn't account for the load, it doesn't account for the restraint effects. Forget about it. We try to do so much detailing for creep and stuff. When the fire happens, we don't account for any of this. Now, that's what my modern buildings are taller, wider, and we have too many of them are coming up all around India right now, for example. And the second thing is our architecture is different. Older architecture, what you need to have, you have a big hole, a small window in that wall. Now, everywhere it's completely glazing. And that glazing goes away at 600 degrees centigrade when the fire reaches, you saw in that curve. So oxygen enters in, it fuels the fire. And everyone, why do we need glazing? So that's what everyone is interested in outside business than inside the room, in their offices. In fact, that's the most competition. You can hire, we hire people, faculty, if they get the office, you know, that's the benefit they get. So it's unfortunate. And fuel inside the room is much worse. My daughter, you know, she must be shopping for her 51st dress. And we call ourselves sustainable. She teaches me sustainability. I grew up with 1 shorts, 2 shorts maybe in India when I grew up. If there is no rain, if there is no sun, next day I have to wear a wet clothes, you know, in the rural village of Kodur. But today, what's happening? It's just press the button and the dress is here. I said, why are you buying this? Oh, daddy, it's on sale. Right? It's on sale. So all these dresses, my son has 20 pairs of shoes. Right? I mean, he wants to go into the gym, right, in the morning. So he, not now, he's studying medicine, is different. When he was home, what happens was he wears a shoes inside the home. He needs, which I never thought of, we have to wear sandals inside. Then he gets into the car, right, different. And because it's snowing, snowshoes is different. Goes to the gym, locker room shoes is different, right? And then plays 10 minutes of basketball, Nike. And Reebok you need for the 10 minutes of volleyball. So he comes back home and he wants to go to a party for dancing shoes is different. I never knew all this, you know. I mean, what a lifestyle we are leading in this world, and sustainable. All these shoes, bad for me is my wallet is gone. That's okay. But much more, that's my stress levels go up because everything comes to my room, my fuel loads are up. Okay. So anyways, modern structures, that's why it's very bad. So these modern materials, whatever we use for these sofas, these chairs, full of plastics, full of, it releases carbon monoxide in fractions of a second as opposed to older wood, right? Remember, wood is much better than steel, for example, from the fire safety point of view, if you don't know. So I think, and you see, I have put this picture here just to show you, this is how much fuel is in this small room. And when it burns and it's full of this, there is no thermal mass. Your structure, doesn't have any resiliency. And this is just, if it works, I will show you this video. The Cladding these days, we put in a lot of cladding, we put in outside. Biggest problem, lot of fires spread vertically very quickly, which we didn't know. It's always, we thought fire and gravity. Sorry. Okay. Can you see how fast? This was not happening before. This is a building in a Turkey where nice condos which were built, fires rise rapidly. This happened last week in Dubai as well. Last week or 2 weeks ago, a major fire in Dubai. So they are changing all, because we are using a lot of this aluminum cladding composites, which was not used for architecture, right? Not for this. These days, it's all how slim you are, how nicely you are looking, then internally, not much strength. You know what I mean? So this is unfortunate. Now see, the fires, electric car fire will produce this. This is most recent work, electric vehicles. Whereas your standard for you, this rapid rise in temperature, remember, watch this, are the bridge fire. That damage is already done, though I think is there. Now, so our structural shapes. Look at this, we are slimming down, as I said. You all know that. With UHPC, your structural shape hardly has any thermal mass. Then, when it comes to materials, we have significant levels of R&D is happening. New materials, steel, concrete, wood. I already told you why we are using. Two problems. One is faster degradation of strength with temperature. You can see in those curves, percentage of strength versus temperature. Higher the temperature, you see that you have normal strength versus high strength versus UHPC. Just focus on that, okay? And we established that recently. And thermal mass is less, you know that. And these concretes have always water. I mean, maybe it's reduced amount water. What happens? A conventional column, normal strength concrete column, can you see here? After 3 hours, nothing happens. High strength concrete, I almost call it UHPC. It's 140 megapascals, doesn't have steel fibers or anything. 140 megapascals concrete, tests were done for Portland Cement Association. So water becomes steam. Here your permeability is 10 to the power of minus 16. It's about 10 to the power of minus 18 or even up to 19. It's hard to measure those times. So water, that steam converts itself into pressure, stress, tensile stress. In fact, if you increase the compressive strength, but not tensile strength very much, when the tensile stress exceeds tensile strength, which is dropping with temperature, boom, 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 popcorn, right? So that's what happens. Now, and it comes out as bullet. That's UHPC beams. You can see on the top, okay? Conventional normal strength of 3 hours. After about 76 minutes, UHPC, okay? So now, what's research can be done? Due to lack of time, I will quickly go through a few slides. Now, we have done a lot of work. For the last 30 years, always my work has been on fire, right? So we tested a lot of beams, columns, slabs, walls, you name it, steel, concrete, any composite, wood, FRP. We tested various types of concrete, did a lot of material properties tests at elevated temperature, about dozen properties you need if you want to model it, not just your strength, stiffness, or elastic modulus, okay? Tensile strength is very important, which we neglect if you want to have a better fire resistance, tensile strength of concrete. Then we developed some guidelines, models and guidelines. So these are some of the mixes. I don't want to go through this. I work with Professor Surushian, some of you might know, to develop this UHPC mix, okay? So these are different beams done for Air Force in the United States as part of an Air Force project. And we develop thermal properties. This is how thermal conductivity changes with temperature. So this is UHPC, this is high strength concrete, this is normal strength concrete. So it's not much, but thermal conductivity of UHPC, if you add steel and polypropylene fibers, you can modify that to some extent, but very much similar thermal properties, you can say, slightly worse in UHPC or higher thermal conductivity, similarly specific heat. When it comes to compression stress strain curves, you can see this at room temperature, 200 degrees, 400, 600, 800, 1000 degrees centigrade, but the rate of heating is different. So especially, that's why when it comes to guidelines, if you are using UHPC in an office building, it's okay. But if you are using in a parking garage where cars can catch fire, if you are using in a bridge, if you are using in a tunnel, you have to do something. I mean, it's danger. right? So that's why rate of heating we first established very recently. Maybe it's there somewhere. In cement and concrete company, we published this paper. Normal strength concretes, you can heat up much higher. I told you what happens in electrical. UHPC and stuff, materials, rate of heating. Many people don't even look at it. That standards don't account for that. So this is tensile strengths as a function of temperature similarly. So we established, and that's the comparison for normal strength concrete, high strength concrete, and UHPC here, high strength here, normal strength here. Okay, so these relations are very important. We followed it with number of tests again for structural members, columns, beams, and all this. I'm going to just show you when these columns were made, the temperatures. For example, one of the thermal response of this, the corner rebar. In fact, in a concrete member, less effect on concrete. It's all how steel is structured, positioned from the fire point of view. When you have this, right? So you look at this, that corner rebar, it sees much more rapid rise in temperature than the middle rebars, okay? And, this is the deflections of the beam. As you can see, this is, if you add polypropylene fibers, it helps to some extent, the deflections, which I'm going to talk about. Then we did the tests, as you can see, right? This is normal strength concrete beam, high strength concrete beam, UHPC beam with steel fibers alone. If you add polypropylene fibers, they melt early at 160 degrees, create channels. Basically, it increases the permeability. Think it that way. And the pore pressure gets alleviated. So you have lesser spalling, much lesser spalling. And they fail, as you see, normal strength concrete beam, it fails in 180 minutes. High strength concrete beam, UHPC, and look at the percentage of volumetric spalling. When you add fibers, you can reduce it, but not fully. We developed models. Lot of macroscopic, we developed our own models starting from Fortran code. And now ChatGPT is helping us well with all this coding, whatever. So with all this, but main thing is we accounted for some of the key parameters. And as you can see in these models, to model how long the column or a beam can survive in a particular fire. That's the idea, right? And we use the material properties we developed. And if you see this, good validation is required. UHPC, you can see the faster rise in temperatures. Normal strength concrete beam, slower rise in temperature. It helps the rebars to maintain to contribute to the tension stress. So normal strength concrete beam on the left-hand side, it's the deflection. Here normal strength, high strength, UHPC with only steel fibers. But if you add it's the opposite. UHPC with steel fibers, if you add polypropylene fibers, you can increase the fire resistance. Okay, so basically, then we varied a lot of factors, which is very important. It's not just the cover thickness and the size as the codes say. So you can quickly glance through this. Basically, I already explained to you, conventional concrete 48 megapascals, high strength concrete, okay, how long it takes for it to fail, right? And how much spalling happens. If you add polypropylene fibers, you can reduce, increase, normal strength concrete beam, it's opposite. Yeah, very less spalling, more, right? So the extent of spalling. Now, basically, effect of cross section, bigger the cross section it is, you get higher fire rate because more thermal mass is there. And so it helps to achieve higher fire resistance. And if you use in bridge girders and stuff, recent project has been with Priestess Concrete Institute, these slender stems is a big problem. Any spalling there, it can happen. It will be just like steel. Okay, when it spalls off in that one, it does. In columns, if it happens, you tend to get biaxial bending. You design this column, axially column, at 15 minutes, you have some spalling because of the huge fire increase in temperature, then you have to include, but currently we don't do that, right? So this is some of the I-shaped columns, rectangular sections, less of a problem than I-shaped sections. And effect of fire scenarios, for example, severe the fire, rate of heating, hydrocarbon fires are much worse if a tanker hits a bridge, right? And then you can see cover thickness. By increasing the cover thickness, you can optimize it, but you don't have much room in a UHPC member. In normal strength concrete member, maybe you have a little bit room. You are losing the entire purpose of using UHPC because your section sizes are limited. So with cover thickness, more the cover thickness is better, only to some extent. So what did we do? We developed some innovative strategies. So first and foremost, one of the project objectives of this one with US Air Force is to remove the shear reinforcement in UHPC, which structurally we have done a lot of work, which you can do because of the higher tensile strength and steel fibers, you can, but not for fire. So don't, if you are doing this for fire purpose, you need confinement is better. You need confinement who helps. Fiber reinforcement, how much to add? Polypropylene fibers, always throw in those fibers. It's not expensive. Talk to material experts. They will tell you the workability becomes problem, but they can come around it. It always helps more than in cracking and other things. And if you are using in bridges and tunnels, combination of steel and polypropylene is much more beneficial than just using steel alone or even polypropylene alone. Then you can do some of these things if you have an option. But Eurocodes and others, they recommend putting a protective layer. That works, but it increases the sectional dimensions, durability, lot of issues. So protective layer, mesh reinforcement, they can help. And we came out, in fact, this paper is going to publish soon, is going to be some design recommendations, how much cover thickness you need. That's not an option a lot of times because of optimized design. If you do this, and what's the minimum dimensions for a beam like this? And what's the cover thickness? Some of the recommendations is both, whether if you have steel fibers alone or if you have polypropylene fibers also, combination. So in summary, UHPC is an effective material to address sustainability, durability, and other things. But I cannot say the same thing unless you engineer the system with some form of, but using codes won't help. Current provisions in the codes. Second thing, it's not just UHPC. Remember, for those of you who have not seen other presentations, any material, if you change the microstructure with fly ash, GGBS, and all this, fire becomes a problem. Similarly, I have a lot of data to show that. Structures made of UHPC exhibit lower fire resistance, especially due to quicker loss of strength and spalling. And you need to innovate it. Through experiments and calculation methods, you can develop innovative techniques such as, I have, even if you are using in columns, bending the ties or providing stirrups, proper stirrups. In fact, closer the stirrups, if you can provide, you can eliminate half of the problem. That's if you can increase the stirrup content, And yeah, the proposed design recommendations can be used, right? And still there is a lot of work which needs to be done to address UHPC. There is a lot of PhD problems for those of you who are doing it. Rather than testing same old compression tests and tension tests, there are a number of things, including bond, shear, for example, strength, for example, creep, high temperature creep. This morning you saw that they are all very much at high temperature, challenging problems. So finally, all this credit should go to a lot of my students and scholars who worked on concrete portion of this or UHPC portion of this, and a lot of support from industry, more than $10 million support both in Canada and US on concrete, overall general concrete projects. So I would like to acknowledge their support and thank you all for your attention. And thanks to Professor Bijli for organizing this excellent conference.
Thank you, Venkatesh, for your amazing talk. It was very, very impressive. And I think you have seen he also burns for his profession. So
I make a living out of fires.
His area of expertise says it all, I think. So now we have a couple of minutes for questions.
Excellent presentation, sir. So I just want to ask you, I'm a practicing consultant in Mumbai. So whenever I advise my client or when my clients used to ask me whether we can go for the UHPC for the proposed hotel project or not. So when I do some basic benefit to cost issue analysis of using the normal concrete versus the UHPC, and within the last digit itself, client told me let's go with normal concrete. So considering the fire application and other benefits of using the UHPC as compared to the normal concrete, is there any thumb rule or any percentage how much it will cost? Like, I just want to understand.
Oh, that I don't know how to answer, but for sure it's more. But you cannot look at just the material cost or design cost. You have to look at the overall project. But you are not talking about the fire, right?
No. By understanding the benefits of the UHPC,
yeah.
But to start with the initial investment for any project, it's been very difficult to make understand to clients to use this for the construction. But the initial cost is high as compared to the normal conventional traditional concrete. So is there any ballpark figure that, let's say, 1:1.5 or 1:2, so that I just want to understand the preliminary one ballpark figure, like how it will be?
Sure, I cannot directly give you an answer. It's more expensive, but you cannot look at just initial costs because that structure might last 10 years in Bombay, especially corrosion, or 20 years. But whereas your UHPC structure might last double the time, right? 30 years. So you have to look at overall, and your material will be much less, and it's much more durable. It's more sustainable. So there are a number of factors, right? And even if there is a fire problem, let's say, you can add some polypropylene fiber, you can easily overcome it depending on the application. I wouldn't recommend for a major bridge without doing anything, right?
And any health monitoring tool going to be used or placed in the UHPC systems?
Sure, definitely. A lot of bridges which are built with UHPC, it's being monitored, a lot of data being collected. Yes, in Canada, I was involved with this project.
Anything you come to know about in India?
No, India, I don't know. Indian, a lot of experts here. Yeah. So definitely you can monitor. Yeah.
Sir, sir, you are like James Cameron, like a big shot Hollywood director. And James Cameron has come up with a movie, is coming up with a movie called Fire and Ash. In next December it will come. So we are all waiting. So when you have that much funding, we are like independent filmmakers, and if you want to quote a budget to a funding agency, they will ask you what is your prior work. First of all, to do experimental work on fire and all, people need to have that equipment. So how do you, like in the Indian context, what can a researcher do in fire?
Sure. No, definitely. I think fire experiments are very expensive. Just to tell you, if you do in a private lab in the US, it's about $35,000 for each of the beams or columns I tested. $35,000. I tested 100 columns, so you can 100 beams over my life. Luckily, thanks to my supporters, National Research Council over funding, and sir, in Canada especially, much more than even in the US, and industry also in the US. I should be thankful. India, for example, that is being addressed 10 years ago, 15 years ago. There was very less interest in India in fire safety and stuff. I am involved with some university, IIT Bombay. Now they want to set up something. IISc Bangalore, over the last 7 years, I work with them. There is a facility coming up. If you want, I can introduce IIT Delhi has some facilities. IIT Bhubaneswar want to set up. IIT Hyderabad has facilities. So as far as I know, and CBRI, more than anything else, I'm involved with them. Right? There is number of places where you can test. CBRI, for example, can address some of the industry needs because they directly test under the code, standard fires and stuff. So there is things happening. Yeah, fire tests are very expensive. And now added to that, you have these modeling approaches. We can use it and use the data from China, US, validate it and apply it.
So there's one final question. No, it's 2 questions. Okay, 2 questions.
Yeah, what is that contributing for low fire performance in UHPC? What is that parameter?
So it's in simple terms, you are closing down all those pores. Remember, UHPC has less voids, so permeability is less. That's the problem in simple terms. One of the spalling, that's why pressure gets accumulated, converts into stress, just like your steam engine, right? The steam engine can pull 1 mile long train. So similarly here, when the pressure exceeds, they escape like bullets, all the outside, keeps on going. Okay. And the second thing is because of the microstructure is changed, the bond between concrete, steel, aggregate, whatever finer or whatever you have, your strength reduces faster than your 1980s concrete, right? All this is a problem.
Okay. We have to go for intermittent and vermiculite, all these things combinations or no?
Yeah, that's good, but who pays for it? It becomes expensive, right? So that's the problem. I think that's one of the solutions. You can put in mesh or outside some insulation. Yeah. So there is a need for those of you who are in industry to develop effective insulation materials for concrete. Going forward, we have to live with UHPC. So there is an opportunity there. Yeah, go ahead.
Yes, sir. My question is that as a structural engineer, we can say we are in two parts. One, the earthquake structural engineer, and one, the fire structural engineer. Because after seeing your lecture, what I understood that, okay, as you are telling, the more mass or the more weight should be required. And as a structural earthquake structural engineer, what we do, we want the slender beams, slender columns, so that the lesser the mass, and we have the lesser the inertial effects, and it would be safer for the earthquake engineer.
Yeah.
Now, last we have seen few months back in the California, Los Angeles, what happened. So there we see that's both simultaneously it's an earthquake prone area as well as the fire. So what you suggest, because we have to sit both the structural engineer as a fire structural and the earthquake engineer, and then they have to decide how they have to build. So what's your recommendation with
Yeah,
that?
my recommendation, it's good. You're a professor?
No, sir. I'm a scholar from IIT Kharagpur, PhD scholar.
Oh,
My
sure.
master's thesis was on
Anyways,
the seismic
you will
effects.
become a
So
professor.
that's why
It's good for all the professors because there is more research needed. More problems are there. Yeah, that's, I think, your combined effects of both, you have to look at it, as well as that's a good idea, right, to optimize it. So currently we are doing age-old prescriptive medicine, right? You don't drink anymore. My mother always calls me from US if I have cold. She asks me to go with, as soon as I have cold. My brother is a doctor. He's a highly specialist, he's a professor in Bangalore Medical College. So he tells me to take antibiotics. My mother says, don't listen to him. Just take some turmeric and then put, whatever, ginger or whatever. She keeps advising me all the time, and I have to take her advice because she's elder, she has more experience. So similarly, that's prescriptive approach. But performance is, my brother targets 650 milligrams of antibiotics, right? It will go, other guys goes for 1,200. So it's this engineered way of doing things. You need to engineer the system rather than, prescriptive approaches work, but not for modern practices, modern this thing. It won't work for us because I'm eating too much. Unlike my father's generation, I'm eating too much. So it may not work for me, for my genes, right? So there is, it is engineered systems.
Okay, thank you very much. For me, the most important sentence of you was, there is more research needed, because then we all will benefit from it. And you have to tell all the government and so on that more research is needed, because otherwise we will not be able to get our aim to reduce our carbon footprint and to be more sustainable. And Venkatesh, thanks again for your excellent talk. And I think we had a lot of fun. And now we know you should reduce the number of shoes to be more.
Thank you. Thank you. Oh,
Thank you, Professor Kodu, for that insightful and engaging presentation. I now request our plenary chair, Professor Novak, to present the token of appreciation to our plenary speakers. I kindly request Professor Novak to come on the dais. First speaker, Professor Ranzi. Next, we have Professor Gettu. Sir. Professor Kodu to kindly come on stage.
Thank you.
I request our platinum speaker, Mr. Anil Kumar Pillai, to please come on stage. Mr. Janaki Raman. Okay. Now I request Professor Gettu to kindly come on stage and present a token of appreciation to our plenary chair. Thank you, sir. Okay. We will now take a break for a group photo session with all the dignitaries and participants. I kindly request all the plenary speakers to come on stage for a photograph, including the plenary chair. Professor Novak, we request you to.
No, he's not here, I think. That's okay, no problem. We are doing good. I talked to a student, they were there the other day as well. So great to have the student.
We will now break for a group photo session with all the dignitaries and participants. Kindly proceed to the ground floor for the photo shoot. I have a small announcement to make for all the participants. You have separate QR codes for both lunch and dinner. So please scan the respective QR codes for each of the session. And also, I would request you all to take a look at the stalls that are set up just outside this classroom. Okay, thank you.